Hi everyone, today we're going to study Pythagorean identities. An equation is called an identity when it is true for all values of the variables involved. Similarly, an equation involving trigonometric ratios of an angle is called a trigonometric identity if it is true for all values of the angles involved. Let us discuss here one trigonometric identity that is called Pythagorean identities. Let's have this right triangle ABC. Then we will use this acute angle A later as reference. By Pythagoras' theorem, we can write the square of side AB plus the square of the side BC equals the square of the hypotenuse, which is AC. Let this be equation 1. There are three Pythagorean identities. Let us derive the first one. Let us divide the equation by the square of the side AC. So equation becomes like this. Then let us simplify. It becomes the square of AB over AC plus the square of the fraction BC over AC equals the right side becomes 1. Now in reference to angle A, AB over AC is adjacent over hypotenuse, that is squared, plus BC over AC is opposite over hypotenuse, that is squared, then equals 1. Remember that adjacent over hypotenuse is cosine A, that is squared, plus opposite over hypotenuse is sine of A, that is squared, equals 1. We can rewrite this equation as sine square A plus cosine square A equals 1. This is the first Pythagorean identity. This is true for all angle A such that A is more than or equal to 0 degree and A is less than or equal to 90 degrees. Let us copy this identity down here. Now let us derive the second Pythagorean identity. Let us divide equation 1 by the square of AB. So equation 1 becomes like this. When we simplify this equation, the first fraction here is cancelled out. It becomes 1 plus the square of the fraction BC over AB equals the square of the fraction AC over AB. Now in reference to angle A, this BC over AB is opposite over adjacent, that is squared, equals AC over AB is hypotenuse over adjacent, that is squared. Remember that this opposite over adjacent is tangent A, that is squared. The hypotenuse over adjacent is secant A, that is squared. Then we will write this equation as 1 plus tangent square A equals secant square A. This is the second Pythagorean identity. This is true for all angle A such that A is more than or equal to 0 degree, but A is less than 90 degrees. Let us copy the second equation down here. Now let us derive the third Pythagorean identity. Let us divide equation 1 by the square of the side BC. So equation 1 becomes like this. Then let us simplify. The second fraction here will cancel out into 1. The first fraction is now square of AB over BC equals the square of AC over BC. In reference to angle A, AB over BC is adjacent over opposite. This AC over BC is hypotenuse over opposite. Remember that adjacent over opposite is cotangent A, that is squared, then plus 1 equals hypotenuse over opposite is cosecant A, that is squared. We can simply rewrite this equation into cotangent square A plus 1 equals cosecant square A. This is the third Pythagorean identity. This is true for all angle A such that A is more than 0 degree, but A is less than or equal to 90 degrees. These are the Pythagorean identities. Example 1. Express the ratios cosine A, tangent A, and secant A in terms of sine A. Let's begin with cosine A. Remember that by Pythagorean identity, we have sine square A plus cosine square A equals 1. Let us isolate the cosine. Let us transpose the sine square A to the right. So we have cosine square A equals 1 minus sine square A. Then we will take the square root of both sides. The left side becomes cosine A equals, the right side is plus or minus the square root of the quantity 1 minus sine square A. Since we are dealing with acute angle A, so the cosine A will take the positive value of the square root of 1 minus sine square A. So this is the value of cosine A in terms of sine A. Then we'll have the tangent A. We know that tangent A equals sine A over cosine A. Now, let us substitute the cosine value from this equation into here. So it becomes tangent A equals sine A over the square root of the quantity 1 minus sine square A. This is the value of tangent A in terms of sine A. Then let's have the secant A. We know that secant is the reciprocal of cosine. So we write secant A equals 1 over cosine A. And from here, let's substitute the cosine A value from this equation. So we have secant A equals 1 over the square root of 1 minus sine square A. This is the secant A in terms of sine A. Example 2. Prove that secant A times the quantity 1 minus sine A times secant A plus tangent A all equal to 1. Let us copy this problem down here. Now let us simplify the left-hand side. What we're going to do here is we express all ratios in terms of sine or cosine. So this secant A becomes 1 over cosine A times 1 minus sine A times the secant A here becomes 1 over cosine A plus the tangent A becomes sine A over cosine A equals 1. From here we multiply this 1 over cosine A by this 1 minus sine A. It becomes like this. And inside, we combine the like fractions. Cosine A is common, so we have 1 plus sine A over cosine A. Let us now multiply the two fractions. So we have 1 minus sine square A all over cosine square A. From here, remember that we have Pythagorean identity. Sine square A plus cosine square A equals 1. We can isolate cosine square A, so we have 1 minus sine square A. Notice that the right-hand value here is the numerator of our fraction here. So we can substitute cosine square A in the numerator. So it becomes like this. The cosine square A in the numerator is now the same with the cosine square A in the denominator. where we can cancel this. So it becomes 1, which is equal to the right hand side, which is also 1. Example 3. Prove that cotangent A minus cosine A all over cotangent A plus cosine A equals cosecant A minus 1 all over cosecant A plus 1. Let us simplify the left-hand side. So the fraction on the left hand we will write in here. Next, we're going to express all ratios in terms of sine or cosine. Looking at our fraction, we will change this cotangent A into sine or cosine ratios. So cotangent A is cosine A over sine A. We substitute in the numerator and in the denominator. Now look at the numerator. The fraction and this negative cosine A have something in common, which is the cosine A. Same is true with the denominator. Let us factor out the common, that is cosine A. So it becomes like this. Cosine A times the quantity 1 over sine A minus 1 all over cosine A times the quantity 1 over sine A plus 1. In the numerator and denominator, common is cosine A. We can cancel it out. And we know that 1 over sine A is cosecant A. So we change it here. So we have now cosecant A minus 1 all over cosecant A plus 1. From here we stop because this value is now equal to the right hand side. Example 4. Prove that sine theta minus cosine theta plus 1 over sine theta plus cosine theta minus 1 equals 1 over secant theta minus tangent theta. Using the identity secant square theta equals 1 plus tangent square theta. Let us simplify the left-hand side, meaning let us copy the left-hand side fraction here. Our goal now here is to make this value equal to the right-hand side. Let us now divide each of the terms by cosine theta. So it becomes like this. And then we simplify each of the fractions one by one. The sine theta over cosine theta is tangent theta minus, this is cancelled out, plus secant theta over, in the denominator is tangent theta plus 1 minus secant theta. Let us rearrange the terms. We can put together the tangent theta and secant theta closer. So it becomes like this. And from here, let us multiply this by the conjugate of tangent theta plus secant theta, which is tangent theta minus secant theta. Same value we will put in the denominator. So what we'll do here, we will multiply this numerator in this group and then in the negative one. So it becomes like this. Tangent square theta minus secant square theta minus the tangent theta minus secant theta. In the denominator, we'll just put them together. And from here, let us look at our identity. We can put together the tangent and the secant in one side. And this constant one, we will put on the left. So it becomes negative 1 equals tangent square theta minus secant square theta. Look at this group here. It is the same with the right-hand side value, which means we can substitute negative 1 to this value here. So it becomes like this. And then let us simplify the numerator. We have negative 1 minus tangent theta plus secant theta. In the denominator, we have this trinomial here. Next thing to do, let us manipulate our numerator. Let us rewrite this as the negative of the group tangent theta minus secant theta plus 1. From here we can see that this value here is the same with the trinomial in the denominator that we can cancel. When we do that, it becomes negative 1 over tangent theta minus secant theta. Let us now rewrite our denominator as negative 1 times secant theta minus tangent theta. So we can cancel the negative 1 in the numerator and in the denominator. When we simplify, it becomes 1 over secant theta minus tangent theta. From here we stop, because it is already equal to the right-hand side value here. This is now the final answer.